Hello.
How's it going?
Good. How are you?
Fantastic.
Good. Welcome. Let's keep plowing forward here. We'll see how long this takes today. I'm not quite sure. We'll maybe have a smidge of time at the end of the hour to work on homework topic 1. At the very bottom of homework topic 1, by the way, it's a 2-pager. Homework topic 1 will be due next week. Tuesday probably sounds about right. Sounds about right. Next week, Tuesday. Today, we're going to be dealing with the equilibrium constant expression still again. Okay, so equilibrium constant is capital K. That is always set up as products over reactants. Okay, and yesterday we introduced Q, which is the reaction quotient. Q is mathematically the exact same as K. The difference is Q uses numbers or values of our reaction when it's not at equilibrium, and K uses numbers or values of our chemicals, reactants, and products when we are at equilibrium. Okay. Towards the tail end of yesterday, what we did was we had some random molarities. We plugged them in and solved for Q, and then we were comparing our value of Q, the reaction quotient, to our value of K. And Q represents where the reaction currently is. K represents equilibrium. If a reaction is not at equilibrium, it will always move towards reaching equilibrium. Okay? So if we had Q being too large, that means we have too many products. And in order to reach equilibrium, our reaction would have to shift towards reactants. If Q was too small, that means we don't have enough product, and we would shift towards the products. Sorry, I'll go in your direction. We'll shift towards the products to reach equilibrium. Okay. Pretty logical stuff. We did a little math. I sprinkled in a slightly different one towards the tail end. Some of the ones on your homework are a little bit different, but pretty logical stuff. Hopefully you felt pretty good about yesterday's class. So let's jump into today. Today is going to combine some of the stuff we learned last unit. Okay. We're not going back to thermal. We're not doing enthalpy today, but we're going to use some of the same concepts that we messed with last unit and apply them to equilibrium. So 2 reversible reactions are performed by a chemist. Both reactions use 0.5 moles of each reactant. I have this first reaction, Br2 plus Cl2 producing that, and then O2 plus N2 plus O2 producing that. I have both of their equilibrium constants. Now, do you see this? KEQ? That's redundant. But sometimes AP will write it that way, or you'll see it that way. The EQ, of course, would stand for equilibrium, but it's capital K, so we already know that it represents equilibrium. I don't know. Okay, I don't know why they do that. It's what you think it is. Don't let that throw you off. This is no different K than any other K we've looked at in the past 2 days. Anyway, so I have 2 equilibrium constants. For the first reaction, the equilibrium constant is 1.0 times 10 to the third. For the second one, it's 4.2 times 10 to the negative 12. By the way, equilibrium constants can get crazy small or crazy huge. All right? We will deal with some equilibrium constants that I think next week, towards the tail end of next week, I think I have one in a problem that's like the negative 55th. Ooh. Yeah, so it's tiny. You know, you just got to write out 54 zeros before you hit that first number. You don't have to write it in scientific notation if you don't want to. You do you. Okay? But long story short, equilibrium constants can get insanely massively huge approaching infinity, and they can get insanely small approaching 0. Now, we're going to talk about the value of this today, and I have this question for you. Based upon the data above, make a comparative statement about the molarities of each of the products and when the reactions reach equilibrium. So this reaction reaches equilibrium, this reaction reaches equilibrium. The question I have here is, based off of those equilibrium constants, would I expect to have more of the BrCl, or would I expect to have more of the NO? remember what K represents, right? K is literally like it's like a fancy ratio of products over reactants. Both of these have reached equilibrium. Which of these two reactions would have more products at equilibrium? The top one. Why? Because K is larger, right? Again, the bigger the K, the more shifted towards the product side my equilibrium is, or my reaction is. The smaller the K, the more shifted towards the reactants my reversible reaction is. So I can just generically look at these. These are different chemical reactions, obviously, different stuff, different things. But I can just generically observe their values of K and make a blanket statement that, yep, I'm going to have more of that product than I would of this product. Why? Because this equilibrium is shifted further towards the product side. Again, the ratio of products over reactants is a large value. It's 1,000. Bigger than 1. If it's bigger than 1, that means the product side is favored. This is 0.00000000000002. Might have been one more, one less. I don't know. But you get the idea. It's small. Really small. So this equilibrium is favoring the reactants. So just generically looking at those two things, I can make a blanket statement that I'm gonna probably have. That's a little off. Hold on. .66% of the screen. That's exciting. And yes, I've tried to fix it a million times. Okay, this is it's got to be greater than this. By how much? I don't know. But just looking at the value of K, that's a pretty safe assumption. Really safe assumption. Again, why? Because the value of K is favoring products for this reaction. The value of K is favoring reactants for this reaction. Questions? So now how can you use that, or what purpose does that serve, right? Literally, if you can just look at a value of K and immediately kind of get a snapshot of what the situation is, that helps. It helps a lot. Just by looking at K and being like, oh, it's bigger than 1. Okay, it must have more product than reactant. That's a good thing for your brain to be able to like do instantaneously when you read a problem. And same thing, right? Or it's like, oh, look, that value of K is really, really tiny. Okay, the reactants are big. Try to get into that kind of frame of mind. Number 2, the initial partial pressure of each gas in the following reversible reaction is 1 atmosphere. After this reaction reaches equilibrium, how would the partial pressures of the N2O5 product and the NO2, one of the reactants, compare? Initially, we have 1 atmosphere of everything. I've got 1 atmosphere of NO3, of NO2, and of N2O5. At equilibrium, how would I expect the partial pressure of the N2O5 to compare to the partial pressure of the NO2? What would I expect? You know how to answer that. Okay, you can say no. Or if you do know how to answer it, you can verbalize your answer. That's an option too. This won't be overly necessary what I'm about to do, but we'll do it anyway. Okay. Is that really necessary to set up Q? Probably not, but whatever. If I did, I would have 1 atmosphere up here. Q equals 1. Obviously, that's very exciting stuff. But Anyway, if I compare Q to K, this is where I am. That's where I want to go, or that's where the reaction's gonna go, I should say, right? So which way do I need to shift in order to reach equilibrium? If this reaction starts with a value of Q equal to 1 and is trying to eventually reach K equal to 2.6 times 10 to the negative 11, which way do we have to shift to get there? We have to shift towards the reactant. Again, if you set up the inequality in alphabetical order, K is less than Q. My inequality will point which way you got to go. We need to shift left. And if we shift left, what would we expect the partial pressure of the N2O5 and the NO2? How would those compare? At equilibrium, what would I expect to know about the partial pressure of these two things? I'm just looking for which one's bigger, smaller. That's all. I'm looking for a comparison, not numbers. It'd be the opposite. Drew, honestly, I sincerely appreciate you trying. That's all I was looking for. Will said it would be the opposite. Yeah, it's the opposite. Now, why? Well, everything starts as 1, right? That's where we are. At equilibrium, we must have to shift this way to reach equilibrium. So if I'm going that way, or this reverse reaction is happening to a greater extent than the forward reaction is happening, what's going to happen to the partial pressure of this as I'm going from right to left? It's going to go down. What happens to the partial pressure of this as I'm going from right to left? It goes up. So because I knew that I started at the same spot for both of them, and because I know the value of K, again, this is another one of those situations where I can just kind of generically or generally look at it and be like, all right, well, I've got to go left. I have to go left to reach equilibrium. And if that's the case, then without a doubt, by the time I reach equilibrium, the partial pressure of that reactant must be way bigger than the partial pressure of that product. It has to be. Follow my logic? Questions? Silent boredom? Okay. Good. Another classic day in chem. Number 3, let's keep going down this rabbit hole. The following data was collected for the reaction below. I have reactant Y turning into product Z. The reverse reaction, obviously, product Z turning back into reactant Y. Initial concentrations. I have 2 molar of Y. I have 0, nothing of Z. Now, if we solve for Q, it's always products over reactants, right? If I don't have any product, what's my value of Q? 0. Which way do I have to go without even remotely thinking about anything? I got to make some product. Hey, spoiler alert, if I don't have any product, I can't possibly go left. Does that make sense? Good. So don't ever say that on a test or something. I've had kids try to claim this to me before. Okay, so if you don't have product, I can't possibly make the reverse reaction happen. That's like a limiting reactant situation again, isn't it? You can't keep going if you don't have the reactant. So, okay, so we don't have to do Q versus K in this one. We already know what that is. I don't have any product. Guess what? We're going that way. We got to go that way. We got to make something in order for this to be reversible. So if this experiment was performed again, same temp, and the equilibrium concentration of Z is 1 molar. The question is, what would the equilibrium concentration of Y be for a second trial? Okay. Hang with me. This is the equilibrium molarities of my 2 things. If I set up K K always equals my products over my reactants. So I will have this as my set. This Z is the product, Y is the reactant. They both have a coefficient of 1, so no powers, nothing weird like that. And I have my molarities at equilibrium, right? So I can just plug those in. I have that Z, I'm sorry, Z is the bottom one. Z is a molarity of 0.8. Y is a molarity of 1.2. So what is the value of K? You can do that in your head, I hope. 2/3, also known as 0.667 or 0.6. We'll use 3/16, I guess. That's fine. That's K. That is the equilibrium constant. Now, if I mess with molarities, right? Because this is saying, hey, they did this whole thing again. But this time, they must have had more stuff because at equilibrium, Z equals 1 instead of 0.8. The ratio at equilibrium will be the same. What I mean by that is, if we have the same temp, that's really important. If you change the temp, the equilibrium constant will change. But assuming they set up with the same experiment, same temperature, just with different quantities, at equilibrium, this is still the equilibrium constant. This is still what we would expect the ratio to be. So we just plug it in again for the second trial. K is 0.667. Z, they told me, is 1. Y has got to be something down there. So it doesn't matter how much stuff I have, right? Whether I start with 2 moles of Y or 8 moles of Y or I don't know, 100 moles of Y, doesn't matter. If I'm using the same temperature and the same setup, the ratio at equilibrium is what it is. This is a constant, right? It's constant under the same conditions. So one trial gave us this ratio. Another trial under the same conditions will give us the exact same ratio at equilibrium. We might have more stuff, we might have less stuff, but that ratio must be true at those conditions. So what's Y? Y equals 1.5, right? Okay, pretty easy, I hope. Again, just a little bit. You got to make sure you get your ducks in a row, I guess, so to speak, in terms of your thinking. But the logic is pretty straightforward. How we doing? These Thursdays are rough. It's like the new Friday, but worse. Because you're in my class.
Wow, Judith, I didn't have to roast
You were mean earlier this week, weren't you?
you. What'd you say? You roasted us, and then I had an awesome comeback. What'd you say? Basically, comeback. Well, what?
That is not what I said.
Wasn't I here for that?
I don't know. I said your decision making is important.
Wow.
That's just facts.
What was the context?
Life.
And then what did you say?
That's my decision.
Oh,
It was good. It was good.
I was trying to
I'm pretty sure I instantly gave credit to that comment. It was a good comment.
ruthless.
It hurt a little bit, but it was good.
That's good.
All right, number 4. Let's keep going. Let's move past this moment. All right. My mask is drying my tears. They're just slowly dripping in there. We have some partial pressures. Those are at equilibrium. Please solve for K. Go ahead. You don't need me. I'll give you a chance to start doing some things. Solve for K given those partial pressures. What do you get for a value of Kp?
-3.
1.6 on 10 to the negative 3? Yes?
Yes.
Okay, cool. Thank you. No, you're good. You're good. Okay, so we calculated K. Let's look at the next chunk here. The next chunk is, if this reaction is reversed, using the same data, what's the value of K for this reaction? Not the same. What do you get? Huh?
Is that right?
I think so.
Oh, big will.
I don't know. I mean, I'm relying on you guys. I can punch it in if you want me
Everyone
to.
got it wrong. Everyone got it.
Oh,
Maybe everyone else got it wrong.
Maybe everyone got it wrong.
what is it? Okay, well, is it wrong? What is it?
Yeah.
6.26 times 10 seconds.
Yeah, that's what
Bro, the ones that are right at, I'm like, 7 decimals.
6.26?
Times 10 to the second.
Did you square the top part? No, no, you must have. Did everyone else square the top part?
Yeah.
You might have multiplied the denominator.
Just use way more parentheses. I put so much parentheses. What? That's true. But.
What I do?
No.
Yeah.
Or we could do it the hard way.
Yeah.
And make it look cool.
The last time I gave him something and it wasn't in scientific notation, he got mad at me.
I don't want to hear the excuses.
Pretty sure I was not mad.
He was angry.
Yeah, I was enraged. Please. Call it what it is. Now, I hope you can very clearly see a couple things. This is the, what do they call that? Reciprocal?
Yeah.
Just making sure I'm not using my math terms wrong. Because what's the difference between reciprocal and like the inverse? There's a difference.
I know it is. I just don't know it.
Yeah, and I used it wrong once, and then a math nerd student yelled at me.
Oh.
Is it interest like the side?
I don't know. I don't really want to know. I
Oh, well,
teach science.
okay, just do that.
It's reciprocal. I knew that much. Okay, so if you take 1 divided by that, you should get this. And if you take 1 divided by that, you should get this. Right? So in reality, if I called this like K1, this second reaction would equal 1 divided by K1. Right? Make sense? That's going to come in handy in a second. The equilibrium constant for the reaction below is 9.5 times 10 to the 1. There you go. You like that scientific notation? I'm kind of glad that happened. What is the value of the equilibrium constant of this reaction? Now, what have we done? From there to here, what has changed? Yeah. So, let's think about what that would do to K, right? This is K for this reaction right here. K equals 95. Okay? 9.5 times 10 to the 1. But in order to get down here, I have to flip the reaction. When we flip the reaction, what did that do to K? Yeah, it's now the reciprocal of it, right? So, okay, I flipped it, so I need the reciprocal, but I've done something else too. I have doubled it. Now, when we mess with coefficients and we double things, what happens to our value of K? Where do these coefficients go when we set up K? Into the exponents. So if I have flipped it, I need the reciprocal. If I have doubled it, I need my K value squared. Hanging with my logic there? So this was K. This one, I'm going to need literally 1 over K squared. When you flip a reversible reaction, you take the reciprocal of the equilibrium constant. Bye, Luca. Have a great day. If you double a reversible reaction, the value of K gets squared. So we have flipped and doubled the situation. We take the reciprocal and square the term of K. So we have this. That means I need 1 over 95 squared. What is the value of the equilibrium constant for this expression? Should be that. Okay. So this is different than what we did last unit, right? Last unit we started messing with Hess's law, and Hess's law was the thing where it's like, hey, look, there's like 4 reactions, and sometimes you got to flip them, and sometimes you got to multiply them by 2 or 3 or cut them in half or whatever you need to do. For enthalpy, delta H, when you flip the reaction, we just needed to flip the sign, right? What was once endothermic turned into exothermic, or vice versa. Positive, negative. If we double the reaction, we just needed to double the enthalpy. So if the enthalpy was negative 500, a doubled reaction then would be negative 1,000. With the value of the equilibrium constant, we can manipulate these reactions in a similar way. I can flip it. I can double it. I can cut it in half. But when you flip a reversible reaction, the equilibrium constant is the reciprocal, 1 divided by what you originally had. When you double a reversible reaction, you end up squaring the equilibrium constant K. Let's say hypothetically, if I was feeling, I don't know, extra fun, let's say instead of going from this to this, I went from, I flipped it, but then I cut it in half. How the heck would I show that over here? What's that? You'd square root it. So if I cut it in half, I would need like 1 over K to the 1/2 power, or 1 over the square root of K. If I tripled it, 1 over K cubed. Okay, so you still take it to the power, right? If you literally took a reversible reaction and halved all of the coefficients, the value of K would be square root. I don't think I'll do that to you ever, but wow. So we can, much like last unit, combine multiple reversible reactions, and we can then combine the values of the equilibrium constant. So here we go. I have these two reactions, and let's add them up. Let's combine these two reversible processes and get a third value of K. I have two SO2s that cancel out. I think that's it. So my overall net result of these two processes happening back to back is going to be 2S plus 3O2 yielding 2 SO3. That's old news, right? We've combined reactions before. We know how to cancel things out and add things up. Same side, you add them up. Opposite side, you cancel them off. But now let's combine these two things. Okay? When combining reversible chemical reactions, we combine their equilibrium constants by multiplying them instead of adding them like we did for enthalpy. So what this really turns into is, because we didn't flip anything, we didn't double anything, we didn't manipulate either of the two steps, right? They just are what they are. We're just literally doing 1 plus 2. But for K, for the equilibrium constant, what we need to do is K1 multiplied by K2. So it's a big number. What do we get? You do that in your head. Yeah, you totally can, right? Yeah. I mean, you got to be comfortable doing that, obviously, but you can totally do that in your head. Or trust the calculator, that's fine too. That's fair. Now, so you can obviously see where I'm going with all this stuff, right? I'm preparing you to do Hess's law using enthalpy or using equilibrium constants. But you do need to be very, very careful because it's different every step of the way, right? We don't add K, we multiply K. If I reverse it, I don't flip the sign, I take the reciprocal. If I double it, I don't double K, I square it. So this process is the same, right? Combining the multiple steps to get whatever you wanted and canceling out and adding up, that's all the same. But manipulating K to get the new value of the equilibrium constant for this, it is different. Be a little careful. You're not adding, you're multiplying. You're not flipping the sign, you're taking the reciprocal. You're not doubling, you're squaring. Okay? All right. Set up each of the following equilibrium constant expressions. K1, K2, K3. Now, when I say set them up, I mean no numbers, right? I just mean symbols. Go ahead. Set those up if you could. Plus, I didn't give you any numbers anyway, I guess, so you weren't going to be able to do that regardless. Okay, and then I say, show how K1 and K2 are equal to K3. Essentially what I'm trying to say there is, right, I can make these two things equal that thing, right? What do I have to do? It's not perfect yet. I got to manipulate something. I think I got to flip K1, right?
I'm just, yeah.
What, okay, hold on. Time out. Let's slow down. This is the end goal, right?
Oh, yep, got it. Sorry. I missed the CH for it.
Oh, you're good. You're good. So this is what we want. So how do I get these two things to equal that? Well, let me take. Oh wait, I gotta flip both. Okay. See, I gotta flip both. So let's flip them both. Now, if we flip both of them, what's that going to do to the value of K? I do what? When I flip a reversible reaction, what happens to the value of the equilibrium constant? Yes, we take the reciprocal. We take 1 over it. So if I flip both of these to equal this third reaction, K3 is going to equal 1 over K1 times K2. Yes? Yes? Okay. So now let's show that with all this nonsense. Okay. 1 divided by K1. Yep, we're doing an ugly fraction. Multiplied by, I'll move my 1 over here. CO times H2O. Over CO2 H2. This equals look like fun? Good. Now let's combine this stuff, right? I have, well, we'll ignore that everything's in the denominator for right now. I understand that we have this weird triple fraction situation going on. Okay, but this CO would cancel out with that CO. The H2Os would combine to give me H2O squared. The H2s would combine to give me H2 to the 4th. So I guess if I rewrote this, I don't know if I really want to, but I'm going to end up with 1 over CH4. Oops, that's not a CH4. Multiplied by H2O squared divided by and that would equal this, right? Is that the same? Yeah, it is, right? I just need to, like, you know, get this out of my weird triple fraction situation. So how do I do that? Well, this, like, yeah. Or, you know, just I know that's what I'm doing, Drew. Thank you. Okay. Long story short, they are the same. Why am I doing that? To show you that reciprocals equal what we think they should equal. We need to take 1 over our value of k in order to combine them when we flip that expression. Okie dokie? One more. I think there are a couple of the charges were wrong on your page. Are they fixed or no? They're definitely not. CO3 should have a 2- charge. H3O should have a 1+ charge. Sorry about that. Just a couple of typos. The CO3 in the second step should have a 2- charge. The H3O in the fourth step should have a 1+ charge. And my question here is, using the equilibrium constants above, write out the appropriate mathematical relationship for the equilibrium constant for this reaction down below. What I want you to do is take these 4 steps, these 4 reversible reactions, and make it equal that. And after you have done so, show an expression of how these k values need to be manipulated so that these 4 can be combined to equal the k value of this. It's Hess's law. Here's my recommendation. Ignore k until you have these 4 steps equaling this 5th step. Start with Hess's law. Start with looking at just the chemical stuff, and then we'll deal with the value of k in just a little bit. Go for it. See what you can do without me. Get those 4 steps, those 4 reactions to equal the 5th. Manipulate them. Flip them, double them, do what you got to do. Good. Always dream of stupid tail. Figured that out in late February. We go down the second meeting. You actually do, that'd be very sad. What about you? On my side. Or maybe not, maybe you don't just turn on like an off. Then you get that beauty. You're gonna say something else for a second. Yeah, graduation's for fools. How's it going? Are we succeeding? Keep struggling. Get it? I bet you agree. Now, here's a recommendation, and maybe you've come to this realization already. You want to find things that only show up in one reaction, right? That makes life way easier. For example, I know when this is all said and done, I need H2CO3 on the reactant side. H2CO3 shows up in the first step and only the first step. And I got one of them. So what am I going to end up doing to the first reaction? Literally leave it, nothing. I don't want to change it, because if I do, then I can't possibly get what I have down here. Now, what you might be having issues with is the HCO3 1 minus. That shows up in two spots. Let's ignore that feller for right now. Huh? Well, but we need one. It is, isn't it? So let's ignore that. It shows up in two spots. Whatever. We'll ignore that for right now. Okay. We need NH3. NH3 shows up in just one reaction. There it is. NH4 shows up in just one reaction. There it is. I don't think I can mess with the third, can I? So the first and the third are locked in. Now the question is how do I get everything else that I need without anything else that I don't need? I have the fourth reaction here. Let's see. So this is good. That's good. I have two waters that I don't want, right? So what should I do? Let's flip the fourth. If I flip the fourth, what happens is I get two waters on the product side to cancel out these two waters on the reactant side. And I also get the OH on the reactant side canceling out that OH, and the H3O on the reactant side canceling out that H3O. Do I need the second step at all? No, I don't. You can ignore it. I have not done that to you yet. You can ignore it. I mean, you don't have to cross it off, but yes, we don't need it. But that kind of makes sense though, right? Like, hold on, let's just take one step back for real quick. We have CO2 or CO3, 2 minus in that equation. It doesn't show up anywhere else, and it's not in the final. That doesn't make any sense, right? I can't possibly use this as a part of my process because I can't possibly get rid of the CO3 2 minus. And it's not something that I want in the overall reaction. So the second reaction, we are ignoring. I have not done that to you yet. You're welcome. I know you're appreciative of things like that. Exactly. And I think we're good. We want this the way it is. We want that the way it is. And we want to flip the fourth. And that should give us the overall process, right? I believe so. Let me just double check. One of those, perfect. Water is going to cancel out with these. One HCO3 1 minus over there. H3O1 plus will cancel out. OH 1 minus will cancel out. And I get exactly what I want. Sweet. So K5, the equilibrium constant of this one, is going to equal what? Correct. I didn't change this reaction. I want that just the way it was. We need to multiply our values of the equilibrium constant. I didn't change the third reaction. I want that exactly like it was. I flipped the fourth. Therefore, I shall take the reciprocal of the fourth. So K1 times K3 divided by K4 would give me the equilibrium constant of this. If I had values for all of these things, I could solve for the value of this by that set. Cool? All right, I am all done. People online, have a lovely day. Thanks for tuning in.
Yeah.